Alright, honors physics students, you might be asking yourself, why do we keep looking at the oppositely charged parallel plates? How come we keep focusing on that arrangement of charges? And of course, you hopefully have an answer. It's because they create a uniform field. Uniform fields are easy, right? No matter where you look between those oppositely charged parallel plates, the field strength is exactly the same, which means the force is exactly the same, which means if we're doing a forces problem with free body diagrams and sigma fields MA, the acceleration will be constant, which means we can use kinematics, and everything is easy. Everything's easy with a uniform field. However, guess what? We're not always so blessed. Now we're going to start to talk about what happens if we have a non-uniform field. Now, we're not going to get into too much detail with this. That's more left for the AP Physics courses, but we certainly do have a brief foray into what happens when we have a non-uniform field, specifically created by point charges, as opposed to oppositely charged parallel plates. As always, we start with a side-by-side comparison between gravitational effects and electrostatic effects. So, here we go. Let's start with the gravitational field. What's the symbol for gravitational field? Hopefully you said lowercase g, not f sub g. No. F is always for force, right? G is for field, and we originally defined gravitational field as force per mass, right? This, of course, says W equals mg because the other name for the gravitational force is weight. This is W equals mg, just rearranged for g. Okay, all fields are produced can be rearranged this way. Fantastic. However, of course, from Newton, we have the equation for the law of universal gravitation, which is capital G, big M, little m over r squared. So I just put that in here, and I divide through by m. Notice this is little m. Remember, little m here is like the test mass. That's U. Capital M, well, that would be like the Earth, the other object in the interaction. And you can see little m goes away, as of course we have our equation for little g, which is big G m over r squared. If we go back to our unit on rotational motion, this is exactly how we derive the equation for a gravitational field produced by whatever mass you put in there. Remember, you put in Earth's mass and radius, you find Earth's field, you put in for the moon, you put in for Pluto, you put in for your mass and radius, you find G there, or of course R could be any other position away from the center, outside the object. Fantastic. Okay, so now we start with our equation for electric field, Fe over Q. Well, I bet you can do this. So why don't you go ahead and pause the video, see if you can go through the exact same steps and derive an equation for the electric field. Spoiler alert, it's going to look an awful lot like this one. Try it on your own. Okay, I'm certain you were successful with that because you're honor students, and at this point in the year, you absolutely can do this sort of stuff. So we're just going to follow the exact same steps, whereas here we replace this with Newton's law of gravity. Now we replace it with Coulomb's law, Q over r squared. We're going to divide both sides by Q. Little q here is the test charge, leaving behind capital Q. So we have E equals KQ over r squared. It has the exact same form, constant object over distance squared, constant object over distance squared. And of course, this object must be the one creating the field. Just like this mass creates this field, this big Q is the source charge. We're going to go right ahead and box it in as our new equation for the electric field produced by a point charge. This equation is only for point charges. It's invalid for any other arrangement of charges. As always, we're going to go through our definitions. So we have E here, the electric field created by the charge. It's always important to know what's doing what job, what's creating the field, what's experiencing the field. In this case, that capital Q is the one creating the field. Now, we are using absolute value one more time, which means this is only going to get us the magnitude of the field. How do we know the direction? Well, we already know the direction. We have all those rules, right? We keep going back to rule 1, which will tell us the exact same information. So when we have this charge being the source charge, we then just imagine our test charge at some location, wherever it is we're looking, whichever way it would feel a force based on its interaction with the source charge. That's going to be the direction of the field created by that source charge. We always go back to rule number 1. Always, always, always. And just to bring it full circle here, of course, capital Q is the source charge. It is the one that is creating the fields, as opposed to the test charge, the one experiencing the fields. And little r, just like before, is the distance from the center. It's not distance from center to center because there's no other object in this equation. We only have the source charge, so it's distance from the center of that source charge. Now, this equation came directly from Coulomb's law, and Coulomb's law came with 2 warnings. Why don't you just pause the video and see if you can remember what those 2 warnings are without looking them up. Okay, in no particular order. One of those warnings was that it's only for point charges or for spherically symmetric ones, which of course is highlighted by, the title of this slide here. This equation is only for point charges. But again, if an object is spherically symmetric, we can imagine all the charges be located at the center, in which case this equation works just the same. However, then we get to warning number 2. This only works for points outside of the source charge. So if we do have, instead of an actual point charge, we have some larger extended object, but it's spherically symmetric, this equation will just not work when you're inside that object. This only works for points outside. And of course, we have the exact same warning on lowercase g back when we did that. What does happen inside? Well, it depends on what the actual object is that's creating the field, whether it's a conductor or insulator. Insulators can be rather complicated. We're not going to get into it at all in this course, but for conductors, you should already know. In fact, we have a big idea about that, don't we? Right? The field is 0 everywhere inside a conducting object. So this equation works outside any object. If it's a conductor, it happens to be 0 inside. If it's an insulator, it's much more complicated than that. We're not going to deal with it at this level. Okay. Let's just make sure we really get how this equation works and how it relates to the previous equation for electric field. So, as always, we go back to the gravitational field equation because we're used to it and we go through the same logic we did before, right? So let's say here's U, that's your mass, and here's your weight. Remember the other name for force of gravity is weight, and this is G. What's creating G? The Earth, right? So here's you sitting inside Earth's field. As a result, you have a force on you, which we call the force of gravity. So here is this test charge. Here's the force it feels because of a field. So this charge is sitting inside a field. As a result, it feels a force. Going back over here. Here's you. Do you create a gravitational field? Of course you do. Is that this field? No. Whose field is that? That's Earth's field. In fact, that field is this one over here created by the Earth. That's the function of this mass. Remember, since the other mass, U, dropped out of the equation, the one that's left there is the one creating the field. So here's you. Here's someone else's field. Whose field? This object's field. So now we go over to here. Here's the test charge. Does it create an electric field? You bet it does. Is that this electric field? Absolutely not. In fact, when we first defined it, we said this is the charge not creating the field, and we said this is the field created by some other charge. What's the other charge? Well, it's the one that didn't go away, right? We got rid of the test charge here. The one left over is the source charge, the one creating the field. Just like this mass creates this gravitational field, this charge creates this electric field. So once again, here's the test charge. It's sitting inside someone else's field. That field is given by this equation produced by the source charge, provided that they're both point charges. We can use this idea. If not, well then we'll have the oppositely charged parallel plates and the other ways to figure out the field, or sometimes the field is given. But just to relate these two equations, this is the test charge, lowercase q, this is capital Q, the source charge. They play their different roles.